the video short is stopped. Now I am starting once again. Let us revise the solutions chapter. Solution is nothing but a mixture of two components. One is solute and another one is solvent. This is a binary solution. A solution with two components is called binary solution. Solution solution the concentration of solution is expressed in different ways. What is concentration? Amount of solute present in a solution. So the concentration methods are mass percentage. Mass percentage equal to mass of the solute by mass of solution into 100. Similarly, volume percentage equal to volume of solute by volume of solution into 100. Molarity. Molarity is nothing but number of moles of solute by volume of solution in liters. Number of moles, how do we find? Given mass by molar mass, W by M, divided by volume of solution in liters. See, it is not necessary to give the volume always in liters. Sometimes milliliters are also given. So if volume is given in milliliters, to change this into liters, divide by 1000. Therefore, VML by 1000. Then molarity formula is weight by molar mass into 1000. Then molality. Molality, it is nothing but the number of moles of solute present in 1 kilogram of solvent. That is, number of moles is nothing but W by M. Solvent can be given in grams. See, solvent is also not necessary to give in kilograms always. Therefore, if a solvent is given in grams, then divide this grams by 1000. That is 1 kilogram equal to 1000 grams. So G grams by 1000. Now molality is nothing but W by M into 1000 by G grams. Then normality. Normality is similar to molarity. Normality, what is the difference? Here we use gram equivalent weight. In case of molar mass, we use gram equivalent mass. What is gram equivalent mass? Let us learn now. So normality equal to number of gram equivalent weights present in 1 liter of solution. That is weight by gram equivalent weight into 1000 by VML. Now, let us see the gram equivalent weights. How do we find the gram equivalent weight? Gram equivalent weight. See, this gram equivalent weight is different for different substances. Gram equivalent weight of an element equal to molar mass by valency. Molar mass by valency. That is a gram equivalent weight. Gram equivalent weight of sodium equal to molar mass of sodium is molar mass of sodium is 23 and its valence is 1. Therefore, it is 23. Similarly, gram equivalent weight of magnesium. Molar mass of magnesium is 24 by valency 2. This is sodium belongs to alkali metals, that is the first group. So gram equivalent weight of first group elements is always their molar mass. Magnesium belongs to second group. So gram equivalent weight of magnesium is 12. Similarly, gram equivalent weight of aluminum. Aluminum molar mass is 27 and valency 3. Therefore, it is 9. So this is gram equivalent weight of elements. Now gram equivalent weight of acids. Gram equivalent weight of acids, how do we find? Equal to molar mass by basicity. Molar mass by basicity. What is meant by basicity? Basicity is nothing but the number of replaceable hydrogen ions. For example, in HCl, HF, HBr, HI. All these are the hydrogen halides. These are referred as hydracids. Also HCN, hydrogen cyanide. In all these acids, only one replaceable hydrogen ion is there. For example, HCl, when it is dissolved in water, we get H plus and Cl minus. One replaceable hydrogen ion. Since one replaceable hydrogen ion is there, their basicity is 1. Therefore, gram equivalent weight of all these is molar mass by basicity. That is, for example, hydrogen chloride. Hydrogen is 1, chlorine is 35.5. Totally molar mass is 36.5 by 1. Therefore, gram equivalent weight of HCl is 36.5. Similarly, we can find the gram equivalent weights of all these elements. Then, all these acids are referred as monobasic acids. Monobasic acids means they have only one replaceable hydrogen ions. Now, dibasic acid, of course, here nitric acid, nitrous acid, HNO2. These are also monobasic acids. Now, let us see dibasic acids. Dibasic acids. What are dibasic acids? Those acids which have two replaceable H plus ions, that is H2SO4, H2SO3, H2CO3. All these are dibasic acids. Right. Now, gram equivalent weight equal to molar mass by basicity. Basicity is 2 here. What is the molar mass of sulfuric acid, H2SO4? Molar mass of sulfuric acid is 98 by basicity is 2. Therefore, gram equivalent weight of sulfuric acid is 49. So, if 49 grams of sulfuric acid is dissolved in 1 liter of solution, then it is referred as a 1 normal solution. Similarly, tribasic acids. H3PO4. Number of replaceable hydrogen ions is 3 here. Then, what is the molar mass? Hydrogen 3, phosphorus 31, oxygen 64. 4 into 16, 64. So, this is 8, 98. 98 by 3. So, molar mass is 98, basicity is 3. Therefore, this is 32.66. This is the gram equivalent weight of acids. Similarly, gram equivalent weight of bases. What are bases? Bases NaOH, KOH. These are monoacidic bases. That is acidity of base. Acidity of base. What is acidity of base? Just like basicity of acid. Number of replaceable OH minus ions. Number of replaceable OH minus ions is referred as acidity of base. Therefore, the basicity of these NaOH and KOH is 1. Now, gram equivalent weight of sodium hydroxide. What is the molar mass of sodium hydroxide? 40. 40 by acidity 1. Therefore, molar mass is 40. If we take calcium hydroxide has two replaceable OH minus ions. Therefore, it is a diacidic base. What is the molar mass? 40 plus 17 into 2, 34. It is 74 by 2, 37. Gram equivalent weight of calcium hydroxide is 37. So, thus we can find the gram equivalent weight, and of course we can find the molarity. Now, if 1 mole of H2SO4 is dissolved in 1 liter, if 1 mole of H2SO4 is dissolved in 1 liter, it is 1 molar solution. 1 molar solution. At the same time, in 1 mole means 98 grams. That is, the mass of the solute is 98. In 98 grams, how many gram equivalent weights are there? 2 gram equivalent weights. Therefore, this is nothing but this is 2 normal solution. 2 normal solution. Therefore, an easy method to convert molarity and normality, that is molarity into molar mass, equal to normality into equivalent weight. So this is the relation between molarity and molality. Molarity into molar mass equal to normality into equivalent weight. So all these formulae may be asked in multiple choice questions or 1 mark questions. Thus the getting marks is very easy. The weightage of solutions in board examination is 5 to 7 marks. Now normality we discussed, and the final one is mole fraction. Mole fraction. What is meant by mole fraction? Mole fraction is nothing but the fraction of number of moles out of total moles. That is mole fraction of first component XA or XB, you can write in any way. XA equal to NA. NA means number of moles of first component by NA plus NB. So this is a mole fraction of total number of moles in the solution, and this is the number of moles of solute. Now this is the most important point. It may be asked as 1 mark question. Sum of the mole fractions of all components is equal to 1. Whatever be the number of components, maybe 2, 3, etc. So sum of the mole fractions of all the components is 1. Suppose 2 components are there, A and B. If the mole fraction of component A is say 0.4, then automatically mole fraction of B is equal to 1 minus 0.4 equal to 0.6. So mole fraction of second component is 0.6. Then finally we have ppm, parts per million. Parts per million equal to mass of the solute by mass of solution into 10 to the power 6 parts. This is parts per million. Million is nothing but 10 lakhs. 10 lakhs means 10 to the power 6. Okay. So this is the mass of the solute present in 10 to the power 6 particles of the mass of the solution. Right. Now, in this way, we can find the concentration of a solution. Now, some important points is if mass percentage and density is given, then molarity equal to mass percentage into density into 10 by molar mass. This is a molar mass. So by using this formula, we can find that molarity very easily. So molarity equal to mass percentage into density into 10 by molar mass. In the same manner, dilution formula. What is dilution formula? If a concentrated solution, say acid, is given, then we have to convert or change that concentrated solution into dilute solution. Then how do we find, how do we convert? By adding the calculated amount of water. For example, M1 V1 equal to M2 V2. M1 V1 equal to M2 V2. Let us check a small question. See, uh, concentrated solution of hydrochloric acid is say 18 molar. 18 molar. Now how much water water should be added? How much water should be added to make 50 ml of 18 molar into say 0.5 molar, 0.5. So here M1 is 18, M1 V1 is equal to M2 V2. M1 is 18, given volume is 50 ml, is equal to M2 0.5 into V2. V2 we have to find. So V2 equal to 18 into 50 by 0.5. This is nothing but 18 into 500 by 5. This goes for 100 times, therefore this is 100 ml. 100 ml of water. See, 100 ml is not the volume of the water, because we are taking 50 ml of the acid. So you subtract 50 ml from this, therefore the answer is 1750 ml. So 1750 ml of water is added to 50 ml, then we get a 0.5 molar solution. The same question may be asked in a different way also. How much solution of 18 molar HCl should be taken to prepare 1 liter of 0.5 molar? So in that way also asked, then V1 is V1 we have to find. That is 18 molar into V1 is equal to 1000 into M2 how much? 0.5. So V1 equal to 500 by 18. 500 by 18 means 250 by 9. 250 by 9. 250 by 9 how much? This is 220 by 18, 70. 70 by 9. 7 times 27.77. So 27 approximately 28 ml should be 27 ml of concentrated salt hydrochloric acid should be taken, and of course it should be added to made up to 1000 ml. That means 1000 minus 28, this is 972 ml should be added. So while doing the problem, just think carefully a little bit, then we get the correct answer. So in such cases, for finding the total final volumes, no confusion should be there. We have to think carefully. So all these are the concentration methods. Then let us see the vapor pressure. Vapor pressure. What is meant by vapor pressure? The pressure exerted by vapor when it is in equilibrium with liquid. So here this is a vessel in which this is the liquid, and of course this is kept with a lid. The solvent, the liquid evaporates. The vapor cannot escape because it is kept with the lid. So the vapor accumulates here. After some time, what happens? The vapor converts into liquid. That means both liquid and vapor, they are in equilibrium. When they are in equilibrium, here some pressure is exerted by the vapor. So the pressure exerted by vapor when it is in equilibrium with its liquid is known as vapor pressure. So the pressure exerted by vapor when it is in equilibrium with its liquid. The pressure exerted by vapor when it is in equilibrium with its liquid is known as vapor pressure. Now, the solvent or liquid is mixed with non-volatile solute. Non-volatile solute. When it is mixed with non-volatile solute, automatically what happens? The vapor pressure becomes lesser because some of the surface is occupied by non-volatile solute particles also. Therefore, vaporization process becomes less. When vaporization process becomes less, the quantity of vapor becomes less, hence the vapor pressure becomes less. Therefore, when a solvent is mixed with non-volatile solute, vapor pressure decreases. Vapor pressure decreases. So this decrease in vapor pressure is known as lowering of vapor pressure. Lowering of vapor pressure. Lowering of vapor pressure is denoted by delta P. Delta P is equal to P0. P0 means vapor pressure of pure solvent minus P. P0 minus P. Now, delta P by P. This is the ratio of lowering in vapor pressure to the vapor pressure of pure solvent, that is P0, equal to P0 minus P by P0. So this the ratio of P0 minus P by P0, this is the ratio of lowering of vapor pressure to the vapor pressure of pure solvent. This is nothing but, this is known as relative lowering of vapor pressure. Relative lowering of vapor pressure. The relative lowering of vapor pressure RLVP is proportional to XB. The XB means mole fraction of the solute. So this observation was made by a scientist Raoult, R-A-O-U-L-T. This is Raoult. Therefore, this is Raoult's law. So Raoult's law states that relative lowering of vapor pressure of a solution or solvent containing non-volatile solute is directly proportional to mole fraction of solute. Right. So XB is nothing but P0 minus P by P0. This is the relative lowering of vapor pressure. Suppose if two miscible volatile liquids are mixed, if two miscible means mix with each other. For example, alcohol and water, they are miscible with each other. Chlorobenzene and bromobenzene are miscible, right? Ethyl chloride and methyl chloride, they are miscible. Therefore, if two miscible liquids are mixed, then what will be the vapor pressure of the mixture? See, vapor pressure of pure liquids A and B are, let us consider P0A and P0B. So vapor pressure of solvent A or liquid A is nothing but P0A, and vapor pressure of liquid B is P0B. Then their mole fractions are XA and XB. Then vapor pressure of these liquids when they are mixed with each other, then what is the vapor pressure? The vapor pressure of liquid A in the mixture is PA, and vapor pressure of liquid B in the mixture is Pb. Then how do we find Pa is equal to XA into P0A? This we call it as a vapor pressure of the liquid in the mixture. It is referred as a partial vapor pressure. So partial vapor pressure of liquid A is nothing but XA into P0A. Partial vapor pressure of liquid B equal to XB into P0B. Then the total vapor pressure of the liquid, that is Pa plus, this is Pb. Pa plus Pb. Pa plus Pb is nothing but the total vapor pressure of the mixer solution is nothing but XA into P0A plus XB into P0B. P0. This is the total vapor pressure. So the vapor pressure and of course relative lowering of vapor pressure, then Rolle's law. Now let us discuss Henry's law. Dissolution of gases in liquids. If a gas is, see, this is our common experience that the drinking water contains dissolved oxygen. Because of the dissolved oxygen, aquatic life is possible. Strictly speaking, 40% of the oxygen is dissolved in water. Now, so amount of gas dissolved in liquid, dissolved in liquid is proportional to molar mass of the gas. This is a mole fraction. Therefore, amount of gas dissolved in the liquid is nothing but a mole fraction of the gas. Now, if we have some daily examples, day-to-day examples, carbonated drinks or fizzy drinks, cool drinks, that is Sprite, Coca-Cola, etc. Carbon dioxide is dissolved under high pressure, and of course cap is kept. So when you shake the bottle and of course open the cap, what happens? The liquid comes out like a fountain because of the dissolved oxygen comes out at once. So in carbonated drinks or fizzy drinks, carbon dioxide is dissolved at a high pressure and of course cap is kept. Now, when a gas is dissolved in water, what will happen? Gas has random motion. Random motion means the randomness is expressed in terms of entropy. The randomness is measured in terms of entropy. When a gas dissolved in liquid, what happens? The randomness decreases. Randomness decreases means entropy decreases. Therefore, when a gas dissolves in a liquid, delta S becomes less than 0. Delta S becomes negative or entropy decreases. Therefore, the decreased entropy is represented delta S equal to 0. Similarly, when a gas dissolved in a liquid, enthalpy also decreases. Therefore, delta H is less than 0. That's why if water is heated, the dissolved oxygen goes out. In the dissolved oxygen, a fish cannot survive because the oxygen is expelled out. Similarly, as a dissolved oxygen is expelled out, it is the water is not as taste as normal tap water, because dissolved oxygen is expelled as it is heated. Therefore, amount of gas dissolved in a liquid decreases with increase in temperature. If the temperature increases, dissolved gas decreases. Now, the amount of gas dissolved in a liquid is proportional to mole fraction, or amount of gas dissolved in a liquid is nothing but vapor, the pressure of the gas. Amount of gas dissolved in a liquid is proportional to pressure of the gas above the liquid. Therefore, XB means mole fraction of the gas. XB is proportional to P. XB is proportional to P. Or P equal to KH into XB. What is KH? KH is nothing but Henry's law constant. So this statement is nothing but Henry's law. Henry's law states that the amount of gas dissolved in a liquid is proportional to the pressure of the gas over the liquid. So P equal to KH into XB. KH, depending on the value of KH, we can understand the solubility of the gas. Greater the KH, smaller is the solubility of gas. For example, if you take two gases, nitrogen and helium. Nitrogen, KH value for nitrogen say 70, KH value of helium is say 80. Now, which gas dissolves to more extent? Nitrogen. Here, what is the statement here? Greater the KH, smaller is the solubility. Because helium has a greater KH value, its solubility is very less. And of course, this is used in application of oxygen cylinders. See, scuba divers. Scuba divers means the divers which the people who go into the deep sea for exploration of different things, they are referred as scuba divers. These scuba divers carry oxygen cylinders. This oxygen cylinder contains nitrogen, oxygen and helium. That means some of the nitrogen is replaced by helium. Why it is so? When they go inside, when the depth of the sea increases, pressure also increases. As people go deeper and deeper sea, what happens? The nitrogen dissolves to more extent in the blood. When they come out, what happens? All of a sudden the dissolved oxygen comes out. Therefore, this causes air bubbles in the blood. Because the air bubbles are created in the blood, what happens? Pain is created in joints. Therefore, these are referred as cramps. So, to minimize the cramps, some of the nitrogen is replaced by helium, because helium dissolves very, very less extent even if the people go into the deep sea. Therefore, these cramps are prevented. That is one of the application of this the solubility of a gas in the liquid, that is Henry's law. Similarly, in higher altitudes, when the people living in the higher altitudes or mountain climbers, they suffer from oxygen because at higher altitude the atmospheric pressure is less. When atmospheric pressure is less, oxygen is also less. Therefore, as oxygen is less, the quantity of oxygen is not sufficient for the respiration or digestion of the food. Therefore, the low content of oxygen in blood leads to become weak and reduce the thinking ability. Similarly, the oxygen, when we when we inhale air has oxygen. Oxygen combines with hemoglobin in the blood. Therefore, we get oxyhemoglobin. So, oxyhemoglobin is formed in the lungs. The oxyhemoglobin goes to the cells where the dissolved glucose is present. So the oxyhemoglobin combines with the dissolved glucose, and we get carbon dioxide and water vapor. Again, this carbon dioxide and water vapor come out during the inhalation process, and of course the released air, if you observe it carefully, the released air is hot somewhat because some energy releases. So these are the applications of Henry's law. Now let us see colligative properties. Colligative properties. Colligative properties. Colligative properties of dilute solutions are those properties which depend only on number of solute particles, but not on nature of the solute. These are the colligative. Colligative properties means those properties which depend only on the number of solute particles but not on the nature of the solute. So the colligative properties are relative lowering of vapor pressure, RLVP, and the second one is elevation in boiling point. Depression in freezing point. And the fourth one is osmotic pressure. Now, we discussed already relative lowering of vapor pressure. Now, elevation and boiling point. For example, the vapor pressure of pure water at 100 degrees centigrade is 760 mm. See, boiling point we defined already. Boiling point of liquid is nothing but the vapor pressure becomes equal to atmospheric pressure. Suppose this pure water is mixed with some solute. Some solute, say salt, say NaCl or glucose, whatever it is. Then what happens? Boiling point increases. Instead of water boils at 100 degrees centigrade, it may boil at 100.5 degrees centigrade. So what happens? Boiling point increases. Boiling point increases. The increased boiling point is shown by delta TB. Delta TB is equal to uh, boiling point of solution minus boiling point of solvent. Boiling point of solvent. Boiling point of solution how much? 100.5 degrees minus boiling point of solvent is 100. Therefore, delta TB is equal to 0.5 K. 0.5 K. Now there is a relation between increased boiling point. This increased boiling point is known as elevation. Elevation means increase. So elevation of boiling point delta TB is proportional to molality of the solution. Molality of the solution. To remove this proportionality, we can keep a constant delta TB equal to Kb into M. What is Kb? Molar elevation constant. Molar elevation constant. Suppose if the molarity is say 1. Molarity 1 means 1 mole of solute is present in 1 kilogram of solvent. If molarity is 1, then whatever be the melting point, elevation and boiling point of water is nothing but the molar elevation constant. Molar elevation constant for water is 0.52 Kelvin kilogram. Kilogram per mole. Kelvin kilogram per mole. So water has the fixed molar elevation constant. Different liquids have different values of molar elevation constant. So this is elevation in boiling point. The next one is depression and freezing point. Depression in freezing point. See, pure water freezes at 0 degrees centigrade or 273 Kelvin. If pure water is mixed with a solute, pure water is mixed with a solute, then what happens? The melting point of the solution becomes 272, that is less than 273. That means the melting point decreases to some extent. So melting point or freezing point decreases. Freezing point decreases. So the decrease in freezing point is equal to freezing point of pure solvent minus freezing point of solution. So this is 273 minus 272. This is only example. Don't consider this. This is 1 degree centigrade is for water, etc. Not that. Just I am giving the example. Right. This is nothing but the depression freezing point. Depression freezing point is represented by delta TF. Delta TF. So depression freezing point is proportional to molality again. Elevation boiling point is proportional to molality. Depression freezing point is proportional to molality. Delta TF is equal to KF into M. Kf is the proportionality constant, and this proportionality constant Kf is referred as a molar depression constant. Molar depression constant for water is 1.86 Kelvin kilogram mole minus 1. So molar elevation constant, molar depression constant for a liquid is fixed. They are fixed values. So this is a molar depression constant. Now let us see osmotic pressure and osmosis. Osmosis. Have you heard about osmosis word? Where you heard RO plant. RO plant means reverse osmosis for the purification of water. Nowadays, every house has a small portable RO unit at the tap to make the water as potable. Potable means used for drinking purpose. First of all, let us see what is osmosis. See here, this is a vessel, and this vessel is made into two compartments, and this is a semi-permeable membrane. Semi-permeable membrane. Semi-permeable membrane, for example, pig's bladder or cellophane, they are referred as a semi-permeable membrane. The semi-permeable membrane has a very small pores which allow only solvent molecules but not solute molecules. So on one side, this is a solvent. That solvent means pure water or say pure liquid. This is a solution. Solution. Or otherwise you can take in a different way also. Solution with high concentration, solution with low concentration, solution with low concentration. When two solutions of different concentrations are separated by semi-permeable membrane, then what happens? Solvent molecules travel from solution with low concentration to solution with high concentration until the concentrations become equal. So this passage of solvent particles, the passage of solvent particles through semi-permeable membrane from dilute solution to concentrated solution is known as osmosis. This is known as osmosis. Right. Now, this osmosis has different applications. For example, flowers. When flowers are kept in air, they lose water. Flowers are kept in air, they lose water in open air. When water is sprinkled or kept in water, when flowers are kept in water, again